For centuries, the building blocks of reality were thought to be immutable. John Dalton proposed that matter is composed of atoms, solid, indestructible spheres with no internal structure. But 20th century physics shatters that assumption. Rub a glass rod with a silk cloth, and the surface develops a static charge that attracts small pieces of paper. If an atom is truly a featureless, solid block, there is no mechanism for it to store or transfer this electrical energy. In 1897, British physicist J.J. Thomson proved that this electricity comes from within the atom itself. He identified a subatomic particle, roughly 2,000 times lighter than a hydrogen atom, the negatively charged electron. Thomson suggested that these electrons were embedded in a sphere of positive charge, like seeds inside a watermelon. The total negative charge of the electrons perfectly balanced the positive sphere, leaving the atom electrically neutral. Thomson's discovery divided the indivisible. The atom was an assembly of smaller moving parts, triggering a scientific race to map the mechanics of its interior. Ernest Rutherford wanted to test Thomson's watermelon model. He designed an experiment to see if the positive charge was spread out evenly. Rutherford aimed a beam of fast-moving, heavy alpha particles at a layer of gold foil 1,000 atoms thick. He expected them to punch straight through. Instead, while most passed through, 1 in 12,000 particles rebounded almost directly backward. The physics of the collision were staggering. Rutherford noted that it was like firing a 15-inch artillery shell at a piece of tissue paper and having it come back and hit you. To reflect a heavy particle, it had to strike something incredibly dense. Rutherford realized that the atom is mostly empty space, with nearly all its mass concentrated in a microscopic, positively charged center, the nucleus. Rutherford's discovery had a major flaw. According to the laws of electrodynamics, an electron revolving in a circular path should radiate energy. As it loses that energy, it would spiral inward and crash into the nucleus, making matter itself unstable. In 1913, Niels Bohr introduced a set of postulates that rescued the atom from collapse. Bohr proposed that electrons are restricted to certain discrete orbits or energy levels, labeled K, L, M, and N. While moving in these specific tracks, the electrons do not radiate energy. They remain stable and locked in place. In 1932, James Chadwick identified a heavy particle sitting inside the nucleus alongside the protons. It carried a mass nearly equal to a proton, but had no electrical charge at all. He named it the neutron. This established the fundamental mechanical blueprint for matter, a dense core of protons and neutrons, surrounded by electrons locked in strictly defined shells. To understand how atoms bond together to form our world, we have to look at their outermost layer, the valence shell. This is the atom's interactive surface. According to the Bohr-Berry scheme, an atom reaches its peak stability when its outermost shell reaches an octet, a count of exactly 8 electrons. Atoms that lack this full count will aggressively gain, lose, or share electrons with their neighbors to complete that shell. This electron transfer is what creates every chemical bond and molecule in existence. We call this drive valency. It is the invisible mathematical engine that powers every chemical reaction in the universe. While the outer shell dictates how an atom behaves, the center dictates what it is. The number of protons in the nucleus is the absolute atomic fingerprint. We call this the atomic number. If an atom has 6 protons, it is carbon. If it has 1, it is hydrogen. No two elements share the same number. The atom's weight, or mass number, is the sum of these protons and the neutrons sitting with them. Occasionally, atoms of the same element carry different numbers of neutrons. These are isotopes. They share identical chemical properties because they have the same electrons, but their physical weights and nuclear stabilities are different. These subtle nuclear variations have massive real-world stakes. We use specific uranium isotopes to fuel nuclear reactors, and cobalt and iodine to treat cancer. The atom is a vast architecture of empty space, governed by strict mathematical laws. It was revealed by a generation of researchers who looked past the surface of matter to map the invisible interior of our world.